Hello, everyone. We'd like to talk to you today about some work we've been doing in the sediments of Falls Lake, trying to help us better understand how processes within the lake affect the supplies of nitrogen in particular that come in and end up often fueling some of the problematic algal blooms. So our title today is Quantifying Sediment Nutrient Processing in Falls Lake. I'd like to thank and acknowledge my co-authors, Suzanne Thompson and Chelsea Brown at the Institute of Marine Sciences, and also thank Nathan Hall, who has been an invaluable partner helping us with both field support and also in collaboration with our work that we've been doing together and that he'll be talking about in the next talk. So we're going to start off talking about the nitrogen cycle. Not the most exciting thing necessarily for everyone, but a really important piece, at least of these next two talks, and really of quite a bit of the discussion around the effective management of Falls Lake. So if you look at this nitrogen cycle, it's one that I prefer. It looks really balanced. It's got all these processes feeding into one another and moving pools around through different, mostly biologically mediated processes. And if you look on the left-hand side, you see denitrification. And what that does is take available nitrogen from, say, a water body and convert it into N2 gas, where it leaves the system and decreases net fertility of the system. I think most people know that the process of denitrification is something that we pay to have happen in places like sewage treatment plants and stormwater management structures, but it's also really prevalent in natural systems. Another one, the flip side of denitrification is nitrogen fixation. And I'm not going to talk about that in my talk, but Nathan is definitely going to in his talk in just a few minutes. And this one's important because it takes gaseous N2, so from the atmosphere, N2, and converts it into a biologically available form. So there's obviously a lot more to the nitrogen cycle, even this sort of simplified one here. But I think the key thing to think about is that there are naturally occurring processes that affect the pools of this really important element that is one of the main things that we're trying to manage and to regulate when we try and get systems like Falls Lake into balance. So what we're going to talk about today is a way to directly measure this process. So these are direct measurements of cores from the lake using water from the lake and getting rates using a machine that I'll describe a little bit later, and the application of those data to the improved management of the system. So nitrogen, of course, is relevant in a system like Falls Lake because things that go on in the watershed of these water bodies change the patterns and magnitudes of delivery of nitrogen. So we're really fortunate in this system that UNRBA has been gathering data for a very long time and has a great set of data on tributary loading and a great set of data on changes in the watershed so that we understand some of the mechanisms of the delivery of nitrogen. And now we're trying to improve our understanding of the processing of nitrogen that goes on once it reaches the lake. So our questions are, what are the rates of sediment denitrification in Falls Lake? Denitrification, as I mentioned, is a complicated process to measure and really hasn't been measured everywhere. So it'll be really important to move forward with improved data in that regard. We want to know how denitrification varies in space and time. So a single measurement from one point in the lake might give you a representative sense of what may be going on in the sediments, but in as big and as heterogeneous a system as Falls Lake, it's going to be more valuable to have measurements through space, so throughout the lake, and also through time. We know that problems that occur in the lake, challenges related to excessive algal growth, are often seasonal. So understanding how this process that may modulate nutrient supplies vary seasonally is critical. And then finally, we want to make a first order assessment of whether denitrification is an important contributor to the overall fate of nitrogen in the lake. I mentioned Nathan Hall being an invaluable asset to us in this project. He was our field guy during this difficult time, coordinated some of our field work, which is sometimes a little time consuming in the field, and we really appreciate it and thank him again. He's also been a great intellectual partner, as you'll see when he gives this talk in a minute. So with our methods, we get cores and we get water right from the system that we're working on, and we take these cores and water back to the Institute of Marine Sciences, where we run what are called continuous flow experiments. And this is a peristaltic pump pulling water from the sites across the cores from the sites and measuring changes in concentrations of dissolved gases and also of the other dissolved nutrients that are conventionally measured. And what your goal is here is to get samples before and after they pass over the sediment surface, see what the sediment has done to modify those samples. And then I mentioned the membrane inlet mass spectrometer, not by name, but just by its role. It allows us to measure N2 gas, which is a really hard thing to measure because more than 70% of the atmosphere is N2. So it's a very big part of our atmosphere. So it's hard to measure small changes in a big pool. And so this machine is really great and has been super valuable to us in a range of systems. And in the end, what we want to calculate is an areal flux. So per area of the lake sediment bottom, how much does it do in terms of removing nitrogen to N2? As I showed you on the nitrogen cycle, that will convert bioavailable dissolved nitrogen to N2 gas, and it'll leave the system. So that will allow us to extrapolate over the surface of the lake and also through time. So this is a figure of our sites distributed throughout the lake along the central axis. Our sites are the same as Nathan's. We have slightly different names for them, and it looks like this may be kind of small, so the name may not be as important in my case because you may not be able to see them. But these are our 6 sites, and we have them from west to east, with sites 1, 2, and 3 in the west on the left-hand side, and 1, 2, and 3 on the east on the right-hand side. And so these are the data from the flux experiments. So N2 flux, if it's positive, that means that nitrogen is coming out of the sediments, and that's denitrification. So in most of these cases, we have positive N2 fluxes. So nitrogen is being removed from the lake by the biological processes going on in the sediments. The scales are all the same here. These experiments were done in the fall, in the spring, and in the summer. And what you'll see is the rates are quite high in the spring, not as high in the fall, and somewhere in the middle in the summer. There's some nuances around our ability to run really effective experiments in systems that, like Falls Lake, have periods of time when they become anoxic. So our summer rates some of them are a little bit less reliable because we were unable to keep the water fully anoxic while we're running the experiments. But we can take these data that are spread throughout the lake and spread throughout the seasons, and we can extrapolate them. And so the darker the colors here, the higher the rates of denitrification. And so this is nice because it gives you a sense of where within the lake are the rates high, and maybe can give you a sense of where the challenges are with algal blooms, where the big loads might be coming in with regard to loading from the tributaries, and begin to say something a little more meaningful about where this biological process of denitrification is important. So at the core, what we found out hilarious. What we found out here was that denitrification, measured directly as we did, removed 45% of the tributary load for the year that we extrapolated our rates. There's a lot more to talk about around that extrapolation, but it's a really good representation of the magnitude of the rate. So potentially really important, but also it'll be mitigated by the fact that we also have to consider the load from the sediment itself, which we'll be able to help calculate as we move forward with our data analysis, and to figure out whether the timing of the removal is in line with when there are challenges with algal blooms. So you want to be removing nitrogen when nitrogen is problematic. So what are the implications and applications? We think that it was a variable, but really potentially significant removal term. We know that models will be improved by the application of these data. We know that the sediment quality measurements will directly inform UNRBA's environmental fluid dynamics code. And we also know that the measured rates will improve UNRBA's watershed analysis management framework and the environmental fluid dynamics code. So we know that there are some direct inputs to the ongoing efforts by UNRBA, and we also know that it's just a broad advancement to have measured data of a process like denitrification. So our plan is to continue our data analysis, and also we're looking hopefully to make measurements in the arms of the reservoir. We think that these arms that are approximate to areas where the nitrogen is coming in could be really relevant to the overall effectiveness of whether or not the process denitrification is contributing to the effectiveness of nutrient removal. So as we have in these talks, we have the one sentence summary. I stuck to really one sentence without tricky punctuation and said that biological processes in Falls Lake sediments remove almost half the nitrogen delivered by tributaries and are relevant to models and management plans. So that's our take home. I'll be happy to talk more about it. The other take home is if you're coming to Falls Lake in your own car and meeting up with a field crew, Make sure you look out for the vultures because they really will eat the rubber from around your sunroof.